Okay, so because we're going to need it later, I'm going to demonstrate at least part of a result. I'll state the result, which is called Stirling's formula. Okay, and the result is about essentially how n factorial grows as n gets really, really large. Okay, and Stirling's formula is essentially the result that n factorial for n really, really big looks like, well, n to the power of n, that's sort of the biggest term, okay, times e to the minus n, okay, times the square root of n, okay, times a constant square root of 2 pi. Okay, so Stirling's formula is quite an important result, as often we'll need to prove results about probabilities when there's sort of really large numbers of events and large numbers of combinations. Okay, and so this formula, okay, is going to give us a good approximation of how n factorial behaves. So one thing to say is when I write this kind of sim notation, what I mean here, okay, so when we write something like this for in analysis, okay, is we're saying that if I look at n factorial and I divide it by this number, okay, square root of 2 pi n e to the minus n, n to the n, if I look what happens to this as n gets really, really, really large, okay, it's going to get closer and closer to 1. So as n goes larger and larger and larger, closer and closer to infinity, this number is going to get closer and closer to 1. Okay? Right. So that gives us an idea of how this grows. It grows pretty fast, doesn't it? Because n to the n is an extremely fast growing function. All right? So probably, you know, by the time we get to 100 to the power of 100, we're probably already looking at more a number that's larger than the number of atoms in the universe. Okay. Now, I'm not going to fully prove this result. If you, it is possible, probably by, you know, a term or two of undergraduate mathematics. So it's a fairly elementary result, or it can be proven in an elementary way, but I don't want to spend a long time. There's still quite a lot of arguments to do there. None of it's necessarily too complicated. If you want to check out a proof of it, you can check the book Introduction to Probability and its Applications, or Probability Theory, should I say. Introduction to Probability Theory and its Applications, okay, by William Feller. And this should be volume 1. It's a 2-volume series of books by a very famous probabilist called William Feller. In fact, this is sort of considered to be one of the first proper textbooks on probability theory, and he gives a great rundown of the argument of why this is true. Okay. Now, he also gives some excellent error bounds on this result as well. So he gives a nice proof if you've got a bit of time on your hands. Okay, but I'm going to prove something a little bit weaker than that, but I just want to convince you why something like this might be true. So prove something a little bit weaker. What I'm going to show is that n factorial is going to be less than n plus 1 to the power of n plus 1 e to the minus n plus 1, and it's bigger than n to the power of n e to the minus n. Okay, so we're sort of sandwiching it between this term and sort of the next term on. All right, so you can see from that we're sort of at least in the right sort of range when we're looking at n to the power of n e to the minus n. All right, so how do you go about proving a result like that? Okay, so, well, one thing we can do is we can take logarithms of n to the power of n. So notice that the logarithm of n factorial, okay, so remember logarithm turns multiplication into addition, so I can think of this as a sum from k equals 1 to n of log of k, right? Because essentially what we're doing when we sum this, it's the same as multiplying inside the logarithm. Okay, now let's draw a picture of log k. All right. So if I draw on this axis, let's say I'll do x here, and then we're going to pop log x, right? So at 1, that function log x is equal to 0. It sort of grows like this, all right? So what this summation is doing is we're going sort of at 1, okay, to 2. If I take the value of log 1, well, the value here is just this. I'll take a different colour actually. Okay. Then if I go at 3, okay, and look at log of 2 and evaluate it for 1 length of time, that's going to, the area under here is going to give me the second term in this sum. And if I go to 4, from 3 to 4, okay, that's going to give me the third, the area under here is going to give me the third value in my sum, okay? So if I do this and go all the way up to k plus 1, okay, then I'm going to get the final value in my sum. Okay, it's got height log k and width 1, so it's the same, oh sorry, log n, should I say, to n plus 1, so it's going to have height log n and width 1, okay, so that's going to correspond to the last term in this sum. Okay, so the value of this sum is just the area under all of these rectangles. Okay, so notice it lies underneath the curve of log x. Okay, so the value of this sum is definitely going to be less than the area under this curve from 1, okay, up to n plus 1. Okay, so what I'm saying is sum of k equals 1 to n log of k is less than or equal to the integral from 1 to n plus 1 log x dx. Okay, now I'm going to draw this picture slightly differently. Okay, so notice now, let's suppose I just shift these rectangles one space to the right. So I'd end up with this being here. I'm just going to shift this over one space. Now shift this over one space. Okay, and I shift this over one space. Okay, and now consider the purple area. Okay. So now I've basically just taken each rectangle and moved it one space over. Alright? Notice that the area under all these rectangles now contains and is above the logarithm curve. Alright? So now we can see this sum of all these terms, when we look at it this way, is actually bigger than the logarithm curve. So it's containing all of this, okay, when we look from 1 up to n. Okay, so with the purple line, what we're seeing is actually that this sum is less than the integral from 1 to n log x dx. Okay, so basically you can get a grapple on how n log n is behaving, n factorial is behaving, okay, by doing this integral. So the question is, well, what is the integral of log x dx. Okay, so what's that? Well, I can just kind of show you what the answer is going to be. It's basically if I can get something that differentiates with respect to y to give the part inside, then I'm going to have the correct answer. So notice if I consider y log y minus y, and I differentiate this with respect to y, okay, I'm going to get one lot of log x when I apply chain rule to this, okay, and then when I differentiate the log y bit, I'm going to get y divided by the derivative of log y, which is 1 over y, okay, so I'm going to get y times 1 over y, okay, which is going to be equal to 1, and then I'm going to get the derivative of this, which is just minus 1, okay. So in the end, what I'm going to get is log y, right? So in other words, okay, the integral from 0 to x, or let's say 0 to n, or let's not do from 0, let's do from 1. 1 to n of log x dx is going to be equal to, okay, n log n minus n. Okay, I should probably be a little bit careful here. I should probably add like a +1 or something like this actually. Yeah, actually that slightly changes my result to the top, but let's not worry about that for now. Okay, so in other words, what I'm going to get here is that n log n minus n plus 1 is less than the sum, well, let's say log of n factorial, okay, which is less than n plus 1 log n plus 1 minus n plus 1, and then we've got plus 1 on again. Okay, right, so now what we can do is remember that the exponential, we can apply the exponential to each of these guys. Notice, because the exponential is increasing, if a is less than or equal to b, this implies that e to the a is less than or equal to e to the b. Okay, so in other words, if I apply exponentials to everything on these sides, it's going to preserve the inequalities. All right, so what I get when I apply the exponentials to these guys is I'm going to get 1 lot of e n to the power of n, e to the minus n is less than or equal to n factorial, which is less than e to the n plus 1 to the power of n plus 1, e to the minus n plus 1. Okay, so I'm basically going to get kind of the result that I had before, okay, that we're going to get an inequality of this type. In fact, I could keep the 1 here because e is bigger than 1, but I should probably add the e onto this side. Okay, right. Okay, so that gives the basic idea of why we get this type of bound when we look at n factorial for large numbers. Okay, so it's going to crop up a bit later. It's going to be useful for us a little bit later. Okay, all right, that's probably enough on that for now. If you've got more questions on that, or you want me to properly go through the full proof, I can probably go through the full proof. Like I say, it's not too hard, it's just there's a lot of it, that's all. Okay, great.